Alright, I'd like to welcome everybody to our online Advanced Motors lecture. This is for MCET 520, Measurement Systems and Controls. So this goes along with the lecture that you hopefully left off on, where we introduce different types of motors and how the different motor technologies work. In this set of slides, we're going to get a little bit deeper into power and efficiency, how these motors work, and how we can really look at and spec a motor. I just want to remind everybody that we should have already talked about this idea of there being different torque points at which we as engineers are concerned with our designs. Specifically, we've talked about this idea of running torque, so how much torque is required to keep our system moving when we're at constant velocity, and this idea of starting torque. This is how much torque is needed to get our system moving. So this is whatever is needed to overcome inertia of our system and to overcome any accelerations in our system. Because remember, and I'm going to say this a lot, torque equals I alpha. All right, so let's dig into this a little bit. And I just want to kind of do a little bit of a visual recap. So here's my problem. I have a mildly large cat, and I want to build an elevator for this cat. We're going to call him Mr. Mew. So I have an elevator platform that my cat can climb on, and that has a cable that goes all the way up to a drum attached to a shaft attached to a motor. And the question is, how much torque do I need to move my slightly overweight cat, Mr. Mew, up a couple of floors? Well, we already sort of know that we have a few things happening here. First, we have Mr. Mew himself, who has a fairly large mass and a gravitational field, so this means that I have a force, and I know that I have that force hanging on a drum that has a radius. Well, torque is that force times that radius. So to lift Mr. Mew, just to keep Mr. Mew moving up towards the second floor of my house, I need to have some amount of torque. Now I also have a real system, so we can also make the assumption that there's probably some sort of friction in our system, and these torques add to that system. So for example, maybe I have some frictional coefficient where the cable is riding against the drum. So I have some F times a coefficient of friction times my radius r, and this too would generate a torque. It's important to note that for bearings, we do this a little bit differently. Usually we have what we call a damping coefficient, which tells us how much torque we need to overcome the resistance of a bearing at any given speed. Okay, so I have a couple of conditions already. I have this static load. Mr. Mew is just hanging out here in space halfway up from the basement to the second floor, let's say. And in this case, I just have force times radius. But maybe I have Mr. Mew moving, right? And he's moving at constant velocity, so he's climbed onto his little elevator in the basement, and he's riding his way up. Well, now I have not just the torque required for Mr. Mew's force at a radius, but I might also have a whole bunch of frictional torques, losses in my system. Again, these things can be bearings, these things can be maybe Mr. Mew's elevator banging against the side, it could be from the cable wrapping around the drum. All right, now something interesting happens here, because the next thing we want to do is maybe, accelerate. We have to accelerate to get Mr. Mew moving because his initial velocity is 0 and he needs to go somewhere. So, okay, well, force is mass times acceleration. This is this kind of linear idea from dynamics, and we can think of this as an analog to inertia. It's really kind of linear inertia. In fact, that's exactly what this is sort of this desire for a mass to not move or really change velocity without an impetus of force. So now I want to get Mr. Mew moving, and I have the force of Mr. Mew, the force due to Mr. Mew's weight, and I still might have all of those frictional forces, but now I have to accelerate Mr. Mew. Now, not only am I accelerating Mr. Mew, I also have to accelerate my rotating assemblies. And this is, again, just a reminder that torque equals I alpha. I being that moment of inertia. You may have seen it as J in some classes. In others, we'll use I. It's one of those things that engineers really kind of will shift their nomenclature based on what they're talking about. So, I want to accelerate Mr. Mu. I have F equals mg, and I also have F equals ma, and I also have torque equals I alpha. And that I alpha exists for, well, let's see, it exists for the shaft, it exists for the drum, it exists for really any rotating component. And something that should stand out pretty quick is these things are not velocity dependent, they're acceleration dependent, which means controlling acceleration means I can control the extra amount of torque. Cool, so I have this static torque, just Mr. Mu there. I have this steady state or constant velocity torque, which is just enough to move my load plus any losses. And then I have this kind of dynamic condition. And these are going to be really important as we go through these slides. So the dynamic condition, right, I still have Mr. Mu's weight, check. I still have all of my frictional forces, check. But I also am accelerating, i.e. dynamic or not constant velocity, which means I also have all of my I alphas. And for complex systems, something where maybe you have a whole gear train, I have to take into account all of those moments of inertia and the acceleration for each of those individual elements. Because remember, again, each one of those requires some torque just to get them to rotate. Things don't want to change velocity. Okay, so this is all well and good. And we've talked about torque, and hopefully you have a general idea of this idea of speed. But now we need to really connect things together. And motors are a class of device called a machine. Generators are also called machines. Things like 4-bar linkages are also called machines. Anything that takes one type of input and converts it to a different type of output, we call a machine. In the case of a motor, we have power coming in and it converts it to a different type of power going out. Now the power coming in, obviously, if it's an electric motor, is current times voltage, P equals IV. This should take us right back to good old circuits 1. Now for the power out, we have torque times omega, and this is kind of one of those like really important, I want to just put this out there so that we all know and we're all thinking about it. Torque times omega. Well, omega is radians per second, and if we use Newton meters for torque, we get Newton meters times radians per second, which works out to be a watt, and that makes sense. If we use something like foot-pounds times RPM, that does not work out to be a watt. That works out to be a very weird and unique unit. So if you plan on doing anything with power that happens to be in the US unit system, right, we'll need a conversion. So for example, you could find out that omega is 2 pi times RPM divided by 60, and then you can find the conversion factor from Newton meters to foot-pounds, and you, in theory, could multiply all of these conversion factors together to get just one number that you can multiply your torque and RPM by in order to convert back to power. Now that was a pretty big mouthful, and unfortunately I don't have a whiteboard to write that, but I can give you an example. If I have torque in foot-pounds and speed in RPM, it works out that my conversion, that 2 pi times RPM divided by 60 and all of these other things, that works out to be 5252. So fun fact, if you have foot-pounds times RPM, you would have to multiply by 5252 to get watts. If you have inch-pounds, that number is obviously different. If you have revolutions per second, again, different. Another reason that engineers really like to stick with our imperial unit system. Also, worth noting that current times voltage is power and current times voltage is a watt, only if current is amps and voltage is volts. So we have to be careful with our units here. Now, if a motor is a machine that converts kind of input to output, that means that not all machines are perfectly efficient. So not all systems are efficient. So we should just take a moment to talk about efficiency. And I'm going to ask you to suspend some disbelief here, and we're going to just assume for a moment until we're good and ready that efficiency for any motor is constant. We're going to find out that that is not true, but this is going to help us kind of form our mental picture first of what is happening inside this motor. All right. Well, we all know that efficiency, that funny looking N called an eta, is power out over power in. So this is our mechanical power divided by our electrical power. However, this can, like I said, change with time. For now, and until we get to our motor plots, we're just going to think of this temporarily as being sort of a constant for any condition we look at. And there's a good reason for this because it's going to really help us sort of understand how that machine is working. Speaking of which, we talked about rotors and about stators and about these coils and these permanent magnetic fields and these things sort of creating these opposing forces that cause rotation. Well, let's take a little bit of a deeper look at that. And you don't need to really write down all the math here. That won't be on the test. But what will be is kind of this conceptual understanding. So follow along for a second. I'm going to grab my mouse pointer here. Hopefully everybody can see this. And here's what I have. This represents my rotor, right? I guess we would call this my armature, the thing that is rotating. So here in the center I have a central shaft, then rigidly linked I have two coils. And I can change these coils. I can make them north or south or north and south, depending on the direction of current flowing through that coil. So let's just take a really small second here and dig way back into physics. We're going to go back into the E&M stuff in physics, and we're just going to reason through what's happening inside of our motor. And again, this is a very basic toy model. So let's focus for a second right up here on this coil, the side of the coil that appears as though it has a north pole. And remember, we're kind of using this north and south here for the EM field as a designator, right? So this appears as though it would be a north poled magnet. That does not mean that there is a north pole magnet there. Okay, so again, I have something rigidly linked at a distance, and this thing is at some angle to this permanent magnetic field. Now in physics we use beta or B as our magnetic field strength, often in something like Tesla's. Okay, so I have this field, and I have this thing that's producing a field, and this thing's field, right, wants to align, ideally perfectly align, with the field between my permanent magnets. So this wants to swing down and click in place and be as close to the south pole as possible, which means there has to be some force pulling it down. And I just want to kind of take a second and say that again. There's got to be a force pulling this down, and that's a force at a distance. So we have some component, right? This is like any good circular motion problem from dynamics. I have some component traveling off tangent to this rotation, and I have this vector component that is this, the field of our coil, and the main field with which it wants to align. And you could imagine that as this north pole swings down and gets closer to the south pole, this force is going to start aligning closer and closer and closer to this field until eventually this force arrow is pointing horizontally straight into the south pole, and our motor is, well, no longer motoring. Okay, that means that we have some component of this force, and that's going to probably be, let's see, I have this that looks like a hypotenuse. I have this that looks like an adjacent. I want that tangent component. This is going to be right here. This would be my opposite. So angle, opposite, sine. So, apologize for that. So this is going to be my sine theta. So the force pulling this north pole off towards the south here at any given time horizontally across the page is going to be the sine of my angle with sort of our inline normal here, right? Like an invisible line between north and south. So that might vary with rotation of the motor, but as that varies, I have another angle over here that's also varying. And we can now begin to see why we might have a different number of either magnets or coils, because if I were really clever, I'd stick on at least one more coil so that as this angle decreases, this angle maximizes, as this angle maximizes, this angle decreases. And on average, I always end up with one of these poles almost 90 degrees to the field that I want. And one of these almost always in line. And that would make this sine term kind of average out to be, well, 1. And this is a really useful fact. Now, all right, if this is spinning and this is moving and I have a force at a distance r causing this thing to rotate, well, how much force do I have? And that comes down to how strong is this field and how strong is this field. If we dig back to physics 2, like really think back, I know that's a rough question here to E and M, we sort of can remember that if I have a coil of wire, the field strength of that wire is dependent on a few things. First, the number of turns of that coil of wire. It's also dependent on the current flowing through that wire. And it's also dependent on sort of the length of that coil, right? So how big that coil is. So how big the coil is, or how long, I guess, my electromagnet is, that's a better way to think of it. How long my electromagnet is, that's my L term. The current going through it, I, and the number of turns of wire on that coil. And if I put that electromagnet near a magnetic field, well then that permanent magnetic field, B, also comes into play. And this really is kind of what is generating that force. This is my basic equation for what is generating my force. So I have number of turns, which I can't change if a motor is built. I have current. Well, I can control current. I have permanent magnetic field strength. I can't control permanent magnetic field strength. And I have length, part of the size of the motor itself, size of the rotor itself. And well, there's nothing I can do about that. So once my motor is built, the only thing I have to adjust my force is my current. So I must have this relationship between force and current. I want you to kind of write that down and hold on to that in the back of your mind, because that is what is so important about this slide, is that we have this relationship between force and current. Another really important thing to point out here is that if I want more force for any given unit of current, I have to make some design decisions. I either have to buy a more expensive motor with much stronger magnets, a bigger B, and this is doable, but it is very expensive, or I need more wire, N, and this causes, some size problems and some heating problems. And I need this, or I would need this to be a longer motor, which might have a packaging and a use constraint for us. So when I'm designing this motor, I really only have just so many trade-offs that a motor designer can make to give me more force for the same unit of current. And you can almost begin to think about this and say, well, this is going to have a performance impact, this is going to have a cost impact, this is going to have a design impact. And that's a pretty cool thought. Now, that's just force, but we have to get from force to torque. And to do that, well, we have to have something. We have to have, again, that sign here, right? So that's just saying, where is this force? Well, this is kind of this force pulling ourselves perpendicular to this radius arm here. So that's the sign. And again, on a fully built motor, not just something clunky like this would average out to be 1. And then also, there's this distance between where my forces are trying to align and the point of rotation. And this is like the width, or I would suppose you would say the diameter of your rotor. So if my rotor has a specific diameter, I can have that. I can find this rotor width and I have this as part of my equation. So this is where all of this force is acting. And this also doesn't help me because now I have another physical constraint that if someone is designing a motor, they're stuck having to deal with, which gives me a control on motor size. So when we want to buy a motor, again, we have all of these pros and cons and all of these trade-offs that we have to consider. All right, hopefully that's had a moment to soak in. Now let's talk about the fun stuff. So I've already mentioned that, we have all of these things that are constants with the exception of current. And I also know that power in, going in, times efficiency has to be equal to my power out. But my power out has torque in it. And torque is dependent on current. And my power in has current. So my torque must be dependent on my current. More current, more torque. And apologies, and sure enough, that turns out to be true. So current is really the only thing I have at hand to get more torque out of my system. So as my torque demand increases, my demand for current increases. And I say that in a very, very specific way because this really is about torque demand. Motors demand current when they need torque. You cannot take a motor and just turn up the current and get more torque at the same RPM. That is not possible. You can, however, give a motor too little current at a given RPM to achieve its maximum torque. Now, I'll run through that one more time because this is a really kind of a nice important concept to have. So I would write this one down. Motors will demand current to try and get the highest torque at a given RPM. Once you reach that point, giving a motor more current will not produce more torque. So there is a maximum here. There is a maximum torque at any given RPM. Okay, now just really quickly looking at this, right, you might say, okay, well, if torque and current are combined, then how do I control speed? Clearly, that's not adjusted by current. I wonder if there's a relationship here between voltage. And, well, the answer there is yes, that's a really good thought. If we preserve power in times some efficiency, and this is why we're just going to say for now we can assume efficiency is a constant, we'll get some power out. Well, let's fix for a moment our current and our torque. Let's not change those, and let's just change the dial that is voltage. Well, as I change the dial that is voltage, that is going to have to change the amount of power coming out of my system. But if I fixed torque and current, the only term that can change for the power out of my system is speed. So with motors, we have voltage and speed linked together, and we have current and torque linked together. So as my voltage increases, so will my speed. And again, there is a theoretical maximum here. The sort of nerdy thought is that as that coil of wire inside my motor, when it's not energized, spins past a magnet or a magnet moves past it, that creates some voltage that goes back into our system. This is how a generator works. And in the case of a motor, this kind of acts as almost an electric brake. So there is this physical threshold by design of every motor. It has to exist that limits the amount of speed of that motor based on its voltage. And again, we know that there's a maximum theoretical torque for any given current. And if you kind of have trouble picturing why that might be, well, if I have a wire, a piece of wire, and I start putting current through it, eventually I put enough current through it and I have something called a light bulb. And we do not want the inside of our motors to glow like a light bulb. All right, so all of this is good, and I want to design a motor, or maybe I want to select a motor, and do I have to sit down and go through a whole bunch of equations to calculate current and voltage and torque and Maybe I have to take and do a dynamometer thing, build something that can measure these. Well, as it turns out, provided you're willing to spend enough money to get a good motor, it will be provided with something that looks like this. And this is what we call a performance curve, or curves, or sometimes a performance plot, depending on who you are and what your industry is. And this is for a brushless DC motor, a small little hobby motor. I think I got these from Pololu. It's a 40 volt 1 amp motor, so I guess maybe not that small, but in comparison. And this shows a whole bunch of different features of our motor, and these plots will come from a manufacturer. So we can walk through this, and that's what I want to do right now, is just to prove to ourselves that everything here looks reasonable. Okay, I have torque on my x-axis here, and we do have to be careful because sometimes manufacturers will put omega down here, but generally it is accepted that we put torque down here. So now I know that for any motor, as my torque increases, my current must increase. So I can look over here and I can see current and I can see torque. And if I have no torque, I still have some current. And at first you go, well, that seems kind of suspicious, until you realize that, well, actually, yeah, I have to get a certain amount of current through my coil of wire before a magnetic field builds that's strong enough to do anything. So there's this little offset here. And this, again, this is not null error. This is there as a function of, well, the physics of a motor. So I put in a little bit of current, 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 and all of a sudden my motor starts rotating. Now I start demanding torque from my motor, or my motor starts demanding current, I should say, from my supply. So as I begin to increase my torque and increase my torque and increase my torque, I increase my current until I hit this like maximum point somewhere up here. And once I've hit this point, well, more current will do me no good. And you might intuitively think, there's this slope of this line here. I bet the slope of this line relates current to torque, and in fact it does. This is what we would call a fundamental constant of a motor. It's usually one of the things that we look for when we dyno a motor. Okay, let's take a look at this black line now, and this is our speed. This is done in RPM for convenience sake. I prefer omega, but I guess we're in ounce inches and RPM, so let's go for it. Now I have this point over here where I have no torque, but I have rotational velocity. And we would call this a no load speed because I have no load on my motor. So now I begin to put more torque on my motor, right? Maybe I begin to start putting a load on the shaft of a motor with a brake or something, right? And again, assuming that my input power is fixed, so I'm not getting more input power, I'm just exchanging speed for torque. These two things were multiplied together to get power. So if my input is fixed, then, well, if torque goes up, speed must go down. And there has to be some proportionality to that, right? This change isn't perfect, but it is constant. It is a very linear relationship. So again, as torque goes up, speed goes down. Torque up, speed down. And then I end up at this point over here, right, where I have this location where I have no speed, but a lot of torque. And we would call this our stall torque. So really quickly, right, if I can get my free running speed and I can get my stall torque and I can get my current at both of those points, I actually have everything I need to really, at the most basic level, figure out how this motor is going to work. Now next I have this green line, and this is my power in watts, and the mechanicals won the tug of war for the plot, so we get to put in mechanical power. So this is mechanical power. Well, okay, well, what is mechanical power? Well, we just said torque times omega, or torque times speed. In this case, there's some coefficient here that we have to multiply by to convert ourselves to watts. But let's just run through this, right? So let me start over here. I have a really high speed, but I'm multiplying by 0 torque. I should end up with a value of 0. Now if I slide over here to where I am at stall, I have a really high torque times 0 speed. Well, anything times 0 is 0. And if I pick any point along here, maybe a 10 here, for example, I'll take this 10 ounce inches, come up, find my speed. I would multiply those two numbers and I would plot them. So it's almost like as I'm kind of moving down this line towards the center of the line, sure, my speed is getting lower, but my torque is getting higher. And since there's a slope of this line, this is going to generate, oh, look at this. I bet there's some calculus involved here, folks. This line with a constant slope is going to generate a parabola. And that is true. This whole parabola comes out of the fact that there is this kind of coefficient that connects torque and speed. And sure enough, there's a point up here where my power should be right about, give or take a little bit of efficiency, right about the midpoint of the speed and torque curve. And yes, indeed, right about there, I would say, is indeed my peak power. And that makes sense, right? Because after I cross sort of the midpoint of this black line, the torque values might get larger, but the speed is starting to get smaller and smaller and smaller. On this side of this point, well, my torque values are smaller, but my speed is still fairly high. So my balance point for this whole thing, my peak power, happens to be right in the middle. And that's a pretty neat and useful fact. Now keep in mind that everybody tries to make this intersection mean something between current and speed. That is a meaningless point, right? We could have milliamps over here and revolutions per second over here, and this crossover point would change. So do be careful when you're reading these. This point here, its position is very scale dependent. Okay, the last thing we see on here is this blue torque and efficiency curve. And this might really throw people for a loop at first, because you might expect, and I've mentioned this, that efficiency would be consistent. And if we look at what we really have, well, efficiency itself is actually not at all consistent. We have this peak efficiency that's at a much lower torque, and then after this max efficiency, we start to taper down, and then we pretty much linearly drop off to a point where, well, we have no efficiency because, well, we're not moving. We might have a lot of torque, but we have no motion, which means we're converting pretty much everything to just heat at this point. All right, well, why is our max efficiency shifted? Well, this has a lot to do with the kind of the electrical characteristics of our motor. As it turns out, putting current through a coil of wire creates heat, which creates resistance, which then requires a little bit more voltage to be able to stand up that current. So at some point, that torque demand starts to drive more current per unit of energy coming in, and we start getting less out. In other words, this side, we are being less efficient and we're converting more energy into heat. This side of this curve, we have not yet used all of our capacity. We're basically leaving some of our input power on the table. We're building these electromagnetic fields and then we're not really using them to full effect. So all motors will have this peak efficiency, and they do not line up with our max power. So again, we have peak efficiency, we have max power, and then the other thing we have over here is this point where we have like absolutely, well, we have nothing going on. We're just heating up our motor. We're getting ready to turn it into melted metal, and this is all occurring at our stall torque. Okay, so here's a question. Pause the video and consider if you were designing, if you're selecting a motor for a system, where on this plot would you want its torque to be under a normal condition? Maybe we're picking that elevator for Mr. Mew. Where would you pick the torque that you want? Would you put it somewhere over here, maybe 25 ounce inches? Would you pick somewhere over here? For any given speed, what torque would you pick? Where on this plot as a designer would you want to live? And where on this plot as a designer would you not want to live? Pause the video, take a moment, and think about that. Okay, so hopefully you've had a minute to think, and there's probably two realizations that you've had. You could design a system so that normally, on average, my torque is going to be somewhere really close to the peak efficiency for my motor. Because remember, I know what my torques are. I know what these are going to be from the mechanical design part. I need to pick the motor. So I might want to pick a motor that gives me the most efficiency. And if what you're doing is designing an electric vehicle or a drone or something battery powered, this is a really good tactic. Now, some of you might go, well, yes, but I expect that I'm going to have a lot of stuff I need to lift. I want to get all the power out of my system. I want to do the best I can. I want to maximize power. And you might have elected to try and spec a motor where this max power point lined up pretty close to the torque that you were going to demand from your motor. And that's also a very viable choice. If you have a system that's going to spend portions of its life, like, fairly reasonable portions of its life, coming up to and running around this max power point, that's reasonable, especially if this is a motor that doesn't move. And hopefully, no one said, well, I will design and pick a motor so that my nominal torque sits out here at a stall torque. That would be very bad and would shorten the life of your motor. And that means that we have this kind of like no-go area. I'm going to call it my bad engineer area. Because if you think about it, right, once you're past your max power, you're putting more electrical power in, you're getting less mechanical power out, you're drawing more current, you're less efficient, and you're going to get less speed. So this is an area that we never really designed to. And in fact, it's not uncommon to see motor plots that just sort of end right here. They just show everything up to max power. And you might kind of squint and go, that's not what I saw in class. Well, actually it is. The people selling the motor just kind of knew that you were a good enough engineer not to pick a design point over here. All right, that is also another nice little important thing, so rewind the video if you missed that, but that is also a very important idea, is that we do not design past our max power. And leave yourself some space if you're taking notes, because we're going to expand on this one more time. But before we do, I just want to take a moment and point out that this is a brushless DC motor, or a BLDC motor. So this is the one that does not have brushes. It has electrical commutation, or kind of like this like AC looking signal coming in, which really means that this is also, I guess we would say, an AC motor. In fact, not I guess, a brushless DC motor is an AC motor. Okay, well, what about other motor types? And as it turns out, different motor types do have different curves. So this, just to be clear, brushless DC motors are what we call a synchronous motor, synchronous AC motor. So brushless DC and a synchronous AC motor have plots that both look like this. Permanent magnet DC motors, well, these are just mechanically commutated versions of what we just saw, so they look pretty much the same. And you'll notice that maybe the max efficiency is shifted over a little bit. It's usually a little bit farther away from the max power, but still, these things look identical. Where things get weird is when we start looking at stepper motors and asynchronous motors. These are the motors that are AC motors that rely on an AC field to build another field. Okay. First, let's just take a quick glance at stepper motors. These are things that are, reasonably important to know, but something you'll want to consult your spec sheet if you need to use one. These motors as well have a relationship between speed and torque, which means they also have a peak power. Suspiciously missing from this is current, and while current is kind of missing because current for our stepper motors is one of these things that those motors will consume as they make a step, but they also consume as they are holding themselves in position, which means a stepper motor that's not moving is effectively 0% efficient. So stepper motors, when they're not stepping, have like no efficiency. They're actually the least efficient motor that you could make. And I want to say that again one more time for those taking notes. Stepper motors are the poorest or have the worst efficiency of any of our motor technologies. When they are not rotating, they are still consuming current, which means they are producing no power but drawing current. The benefit again, though, is they will hold against a load. So we don't really think of it as stall torque so much as holding torque. Okay, so there's a reason we don't have current plotted on here because it's, not irrelevant, but it is not as relevant as we would think. These steps and the speed are really controlled by coils flipping, not like traditional current. The other thing that like I talked about, just said, is that he's suspiciously missing is our efficiency, because whenever these things are not moving, they're not efficient at all. So sometimes you will find maybe an efficiency plot, but it's usually not something we're concerned about. With stepper motors, what we are concerned about is what we call our start and stop torque and our pull out or pull in torque. And start and stop torque gives us how much torque we need to do exactly that, start or stop an unloaded, disconnected motor. So again, if you think about it, right, we have the center part of the motor that's rotating, just like any other rotating part, that has inertia, which means, well, okay, cool, there has to be some inertia to get the rotor moving, to get the moving part moving, and we also have to be able to stop that, and stopping a rotating thing requires torque. So this shows us the torque to start or stop a motor at any given speed. For this specific stepper motor at any given speed. So these are the speeds at which I can easily just stop my motor without having to worry about it kind of coasting. Another fun fact, look what they did to us here. They put torque on the y-axis, speed on the x. I told you that these motor designers are crafty people and they will keep you on your toes. All right, last but not least, we have this thing called pull-out torque. And remember that a stepper motor is kind of constantly locking into place. So it's making all of these little locked steps. Well, if you want to, change its speed, or at any given speed you want that thing to change, it requires a little bit of torque to get that change to occur. So if I am at, for example, let's see, what do I have here? Right around, 2,000 RPM. I need, 1.49 millinewton meters in order to be able to get this thing to really start having any speed change. And again, that is a unique thing to the way steppers are designed. Asynchronous motors are a whole nother deal entirely. These are ones that operate on this idea of slip. So we have this permanent coil that forces a magnetic field in a spinning coil, so that one spinning coil is sort of chasing this magnetic field around. They can never get faster than the moving electromagnetic field, but they always can run slower. And for that reason, these things have this really unique torque curve where they have this point where, you can't get, again, look at speed here, you can't get a motor to move and you need some torque to overcome that. This is a locked torque. Then we have this torque at which we can really begin to increase speed. This is our pull-up torque. Then we have a torque at which we're going to exceed the motor's ability to produce anything. So over here, right, we're kind of on this downhill side. We have this thing happening where we have speed, but we've lost all ability to produce torque. All right. These two, by the way, again, I would just know that they exist and kind of some of the broader concepts. Really think about PMDCs and our brushless DC curves. All right, we're almost done. We have just a few more slides to cover here. This isn't a very particularly long lecture. I just want to give you some last thoughts as an engineer who might be designing something with a motor in it. And my last thought is that, as it turns out, for designing a motor, especially motors that use BLDCs, so brushless DCs or permanent magnet DCs, or what we call synchronous AC motors, kind of our common AC motor, we have this rule of thumb. And the rule of thumb goes like this. So if I look, I have speed and torque. Thank God torque is back on the x-axis. At least it feels normal now. And when we design our motor so that our continuous usage is often 30% or less of our stall torque. So these percentages are referring to our stall torques. So we would like to pick a motor where, when it's running, constant velocity conditions like normal day-to-day usage exists in this 30% or less. And if you think back to our little graphical approach here, it kind of looks like efficiency would fall into that zone. And indeed, that is what this is trying to get across, is that this is where most motors are efficient. We typically like to design continuous usage near efficiency. Now, maybe something happens, right? Maybe Mr. Mew has caught a extra mouse, or maybe he's particularly large this morning. He ate a big dinner, and for just a brief period, we have to get this larger than normal mass accelerating. Or maybe I'm designing this as the continuous usage for moving Mr. Mew is his constant velocity condition, but I do need to accelerate Mr. Mew. And this is what we would call intermittent usage. And this, we're normally okay with having this intermittent usage enter this region of 30% of our stall torque to 60% of our stall torque. And again, take a moment and think about where this lands on our kind of performance plot. And yes, for sure, that sort of lines up around our max power point. So again, this rule of thumb is just trying to say, listen, I'm okay being in this region intermittently, especially if this is where my max power lives, but on day-to-day usage, I really want to live over here near efficiency. Now, it's also saying that really, I don't ever really want to use more than 60% of a motor's rated torque. I can, but it's really bad for the motor's long-term operating, right? Like I'm heating things up, I'm stressing components, and I'm really getting no benefit. So this, again, I would argue maybe a little bit on this side of that 60%, considering peak power is about here at 50, but again, past the 60% mark, we just consider this to be a no-go area for good engineers. All right, so this is sort of my first rule for designers. My second rule, or kind of thought for designers, has to do with stepper motors. And if you can't tell, these things like to break the rules. That is basically what they do. All right, first thought. Everybody here has probably heard, oh, that's a NEMA 17, or oh, you have a NEMA 14, or, oh, it's a NEMA 12, when talking about stepper motors. And NEMA, N-E-M-A, is a physical size packaging So this is like a kind of a manufacturers association, which is mostly manufacturers in the U.S. who build these types of motors. And what they have agreed upon is that there should be a standard mounting pattern. And that's it. Yep. Has nothing to do with the shaft, nothing to do with the length of the motor, nothing to do with the power, the performance, the speed, the configuration. All it means is the mounting pattern. In other words, a NEMA 17 motor of any length, shape, shaft size, dual shaft, notched, keyed, splined, any length will fit the same mounting pattern as any other NEMA 17 motor. And this can be very frustrating. So it always pays to pay attention if you have to use stepper motors to start with that mounting flange design and work your way back into other requirements. Okay, well, the other thing we have to talk about, and I would be really remiss if I didn't, and this also is a stepper motor sort of deal, is that most stepper motors come in increments, right? Step angle increments of 1.8 degrees or 0.9 degrees per step. And this has nothing to do with something called micro stepping. This is just how many steps by design, the way they are built, do these things work. So we can kind of do the math, and this is exactly the math we would find if we were looking at a rotary encoder, except instead of the number of pulses, we just have the number of steps. So I have 360 degrees in a revolution. If I have 1.8 degrees per step, I have a motor that has 200 steps per revolution. And that's a nice little thing to know, because this is the kind of the default, I'm going to call it default accuracy that I could achieve with a motor. Now I can play other tricks, and these tricks will be calculated differently. I could have something called micro stepping, for example, and I'll briefly post a little bit of a lecture for those who are interested, but this allows me to increase the resolution of my motor. In other words, I could have 2x micro steps, which takes my 1.8 degree stepper and drives it down to 0.9. I could have 4x, I could have 8x, so on and so forth. Just a fair warning though, as I increase the amount of micro stepping, I decrease the torque available, and that is usually very considerable. Okay, that's all I have for you today. I did promise kind of a short little video lecture, and I want to thank you for your time, and have a wonderful day.